included. So for any smaller time, this is already included in the big set. So if you add them together, in addition to the big set, you just get the big set. So this is R sigma 0 in exactly time t. Okay? So what is R sigma from 0 in general? What is that? What's that? So now we're talking about forever. What you get? So enlarge T and get bigger set, enlarge T and get bigger set, and
But the bottom boundary is going to always be the same.
very good. So it's everything that is y greater than or equal the bottom boundary, right? And maybe you can add, yeah, it's already there. The origin is already there. Okay, this is the second example with some digression. Let's take a third example. We're trying to change here from 1 to 2, we change the control set. Here, let's change the dynamics. So we have x dot equals u, but y dot equals 1. This is example 3. Let's say the same state space manifold. It doesn't matter, u can be, let's have it R. No bound. X and y. What's the reachable set in the origin in exactly time t? What's that? What about x?
R.
Very good. So x is free. What about y?
T.
Yeah, y, there is no freedom at all. Y is just t, and yeah, so that's it, right? So it's just slice. This slice, okay? So what is R sigma 0 less than or equal t? So do it with a smaller t, you get a smaller line or line below, another t, another t, another t, of course it's continuum, and add them all together. What you get?
Slice of the positive half plane.
Yeah, so x is free, okay, and y is positive, correct? And because we're doing the union including t equals 0, I will also have this guy. I will do union with the origin, right?
But y has to be less than t, right? Bigger than 0 or less than t.
Yeah, that's right. So 0t. Let's see if 0 is closed or not. Yeah, we were doing the union, right? So actually, I don't need this guy.
But this includes any point on the x exceeds, which does not belong to the reachable set, right?
Yes. So we will
Then we need to exclude the 0 and
this one and add the origin.
okay,
Very good. And if we say R sigma of 0, everything will be the same, right? Except this is just t will go to infinity, so y is greater than 0, right? Also union the origin. Any questions about that? So this is an example where these two sets, they are not equal. Let's change the state space manifold here. So the same example. So x dot equals y, x dot equals u, your control, but y dot equals 1 also, it's the exact same dynamics. The manifold now is not R2. The manifold is S1 cross R, or R cross S1, doesn't matter. So, and the u, let's constrain it from -1 to 1. So your thing is a cylinder, right? So let's say this is x, so x is positive upward, x is negative downward, and we have another coordinate theta, lives on a circle. So you can actually name this guy as theta instead of y. So this is theta dot as well. Okay. So it's the same dynamics, but I'm just changing the manifold. What is the reachable set from the origin? This is the origin in exactly time t. This is really not very different from the previous example. It's every x and y in the manifold S1 cross R such that. What about x? So in exactly time t, and you have bounded control. What about x? Minus dt, very good. And what about theta? What about theta? T, right? So it's very similar to what we had before. So x is from negative t to t, and theta is just exactly t. What about the r sigma 0 less than or equal to t is?
Professor, shouldn't we say theta is equal to t mod 2 pi? Or
It doesn't matter because in S1 they are equal by nature, right? So for here, if you have lesser t, well, all the points are included here for x, and for theta, you will keep adding them, so it will be between 0 open to t, right? It's like that, similar to example 3. But what about r sigma from, so the entire reachable set? If you let time go, what's the entire reachable set here? What is the entire reachable set?
It's the whole manifold.
Yeah, very good. Every point is reachable. Give me any point. Do you like this point, for example? Okay, well, I can get its x fine if you give me some time. And also, if I let the dynamics evolve, eventually I will get to this angle, right? So, look at this here. In this example, we have an unbounded control. It's the exact same dynamics. Unbounded control. Here, I have the exact same dynamics, and I even bounded the control, yet the set of reachable sets here is the entire manifold. Over there, it's not. Okay? So, really the manifold structure plays a role, and unfortunately, there is no, very few analysis tools, almost none, that can capture this kind of thing. You have to get it on your own.
Yes, Professor?
Yes.
But this trick is due to that the
Manifold.
second variable is belonging to S1,
Yes.
not belonging to R.
Yep. This is what I'm exactly what I'm talking about, right? Is that it's due to the manifold nature. This lives on a cylinder, doesn't live on R2. It's only because of that we got the reachable set the entire state space, even though we have a bounded control. Okay, so now we will, after this story and this kind of thing, we will relate to an essential question. By a control engineer. Can I do all maneuvers or motions for my system? Can I achieve these? This question is exactly a controllability question. So given some point, this is an equilibrium point or an operating point for an airplane, for an oven, for whatever. Given an operating point for your combustion chamber, whatever, you name it. Given an operating point, can I go to all possible? We want to do control from this operating point. Can I go to all possible x final from x node? Very legitimate question, right? This is exactly the controllability question. It's a very important question. Why? Because if the answer is no, what are you going to do? The answer is no, as a control engineer. If you found no, there are some states that are important and possible to achieve, but I cannot. I should be achieving it physically. There's no, nothing prevents me from doing that, but my design does not allow going there. What are you going to do?
Re-engineer.
In what sense? What are you going to do?
Add some control.
Yeah, add actuator, right? The decision is serious. You're going to add an entire actuator to your system to make it functional, and then you're going to go and try to answer the same question again until hopefully the answer is yes, right? If the answer is yes, what do you conclude? So if it is from the beginning, I check this question and the answer is yes, I can go to all, I can achieve all maneuvers, all motions, I can go to all possible points. Yes, are you happy with that?
Maybe you can optimize the time that you can.
Very good. We can still try to, do something about it, try to optimize, because I have now to answer the following questions. Do we have extra actuators, right? It's not a good design if I can achieve all maneuvers and I have tons of actuators. This is not a good design. But if I don't have extra actuator, that's great. If I do, yes. What are you going to do now? I would remove one, right? To make my system really functional in an efficient manner. An actuator means extra weight. We are airplane designers or aeronautical engineers always obsessed about weight, but it comes with many other stuff than the weight. So I will remove an actuator, and I will try to answer this question again until I satisfy this criterion with the minimum possible actuators. So the answer here is no, then this is really a good design, right? Okay? Any question about that?
When you're going to the no branch, are you considering, no, the right one. Are we already considering, for example, what we learned from differential geometry, in which we have no linear?
I'm going to exactly to this point. So exactly to this point now, to answer this thing. I have a linear system. X dot equals AX. So this is my drift. It is just linear in the states. AX plus B1U1, BMUM. So these B's are my G's, control vectors. They are just constants, constant G's. So if you collect them, please, here, X dot, X dot is, this is a matrix already, times X's, plus if I collect all these vectors, B is, it will give me a matrix B, times U1 up to UN, right? And the powerful thing is that I have an analytical solution. The analytical solution, x of t from any x naught is e to the at times x naught plus the variation of constants formula. E to the at minus tau, b u of tau, d tau. Right? Okay. So now I can answer this question in an easy manner. Why? Because if you're giving me some x naught and you're asking, can you achieve any x final out of this x naught using some control, this question boils down to the following operator. This operator, L, that takes a vector in the control set and gives you a vector in Rn, right? This operation on U takes a vector and finally gives me a vector in Rn that will be added to this guy, giving me the x final. If I want to reach any x in Rn, then the range of this operator must be Rn, right? So I need the range of L to be Rn, which is a bit hard to characterize. Luckily, the range of Rn, the range of L, is exactly equal to the range of another operator, W, which we call the controllability gradient from 0 to t e to the at b transpose e to the a transpose. This is tau d tau. Why this is better? Because this doesn't involve any U. This just involves A and B matrices of your system. It's in terms of the things characterizing or defining your system. This is the controllability gradient. If you want full range for L, well, you need to have full range for W. And luckily, this is the contribution of Kalman and his co-workers. The range of W is Rn if and only if the rank of the controllability matrix be AB, A squared B, and so on, so AN minus 1B is full rank N. So, okay, the controllability for linear systems is characterized by what I call a paradise. Why? Because it's very easy check to do as an engineer, just getting some matrices and checking the rank, and it's necessary and sufficient. Well, you can ask for better, right? Necessary and sufficient and easy check. So what made this process successful? If you look at it just in a single slide, what made it successful? What really made it successful is the analytical solution, right? Then we have an analytical solution here that I started with. And what else? Yeah, so given this analytical solution, what else? Look at the language. This, by the way, this thing is in 270A. If you want to learn about this stuff, this is what you study in 270A. Given this analytical solution, look at the language that we kept using. The range, rank. What language is this?
Linear algebra.
Linear algebra. Very good. So we have abundant tools in linear algebra that allowed getting this very, this is used everywhere, the controllability check. So now let's go to nonlinear systems. Okay? So we have x dot equals f of x